Okay, thank you everyone for coming today. We have Professor Driggs-Campbell to talk to us about designing interactive robots and how it relates to CS. So take it away.
Well, thanks for having me. So my name is Katie Driggs-Campbell, and I'm an assistant professor here at UIUC in both the electrical and computer engineering department as well as computer science. So broadly speaking, my work looks at how we can design safe robots that are going to operate out with people in the real world. So we consider how to understand how humans will behave, determine how these robots should move and interact with us, and develop tools to assess safety. So today we're going to talk about general robotics and think about some of the challenges that come up when we're designing these systems. So before we jump into some of the more sort of technical stuff, one of the questions I really like to ask when I talk to folks about robots is I like to ask them sort of where they have seen robots or which robots they've actually interacted with. And not too long ago, almost all of the answers that I got were something along the lines of these guys. So almost all of the robots that people had seen and interacted with were from movies or TV shows. And on the screen, the robots were able to do these really amazing things. So they could perform tasks with superhuman skill, and all the while, probably not always, but generally they were also being very likable and interactive. While these robots are fairly far off, we're now getting to the point where when I ask this question, people have actually seen or they know about some robots. So some of the most common sort of commercially available robots are things like the robot vacuums, like the Roomba, or self-driving cars. And while these robots are awesome in their own right, they're still fairly constrained, right? So they operate in fairly well-defined environments and controlled settings. And they often do encounter problems and their own challenges. So today, hopefully, we'll talk about what some of those challenges are, and hopefully we'll give you some of the ideas and things so you can start thinking about what some of the challenges they might encounter might be. Okay. So even if we don't actually physically interact or see robots on a daily basis, there are lots of different robots that are working behind the scenes to make our lives easier. So here are two examples from my lab. So this one that already played was an agricultural robot. So let's see if we can get this to play one more time. So this is a robot that basically will go up and down corn rows, so it can collect data about how the plants are going and get basically more information than a human could due to its like precise sensing and information processing. On this other side, we have these manufacturing robots. So I can play this video here. So while these agricultural robots are relatively new, manufacturing robots are very, very common. And it's probably one of the most prevalent use cases of robotics today. So most robots are these robot arms or these manipulators, and they're very, very good at these really rote, repetitive tasks that require these really high levels of precision. And they're really good at basically assembling these things that we do interact with and use every single day. So these sorts of systems are assembling our cars and our electronics, and even though we don't actually see them, they are influencing our lives. So let's talk a little bit about the different pieces that basically go into making either of these robots or any of the other ones work and operate in the real world. So the example that I'm going to talk here is focusing on autonomous vehicles, but in reality, this everything that I'm saying should hold for robots in general. So basically, to make any of these systems really work, it requires many different pieces and many different modules to basically come together and work in harmony. So first, we start out with our robot platform or our hardware system, and this will be equipped with some sort of sensors. So these sensors can be things like cameras, bumpers, radar, LiDAR. These are basically things that basically convert something in the world into some number and allows the robot to detect what's going on both internally. So this can be something like whether or not the wheels are moving, the velocity or heading of the robot or the system, as well as external sensors. So again, things like cameras and whatnot that will help us do things like detect whether or not there are obstacles in the way. So all of this information, so again, these sensors turn this observations of the world into some sort of number, some sort of sensor reading. And this is going to get passed down to our perception system. And our perception system is basically going to be what takes all this raw data, which again is just sort of some number, and turns it into something meaningful. Okay, so for example, our perception system might take something like an image, which is basically just a collection of different color values or numbers, and it will try to understand or interpret this image and turn it into something like an indication or tell you whether or not a pedestrian is nearby. So these two sort of components in our robot are highly correlated or related to an area in AI called computer vision. And this is basically the study of taking the sensor information and helping the robot see or make sense of the world, very similar to the way we as people do. Okay, so this perception information and basically what the robot sees should get passed down to and there's an image of some of the computer vision. So again, we want to take this image and press it down. So this information gets passed down to something like a decision-making module. And this is basically what's going to help us turn these this perception information into some sort of actions that will allow the robot to interact with the environment. And one of the key differences between robots and sort of traditional algorithms or AI systems is that we really want to be able to interact with and influence the physical world. So this is basically our first step in taking this sensor information and turning it into actions. So these decisions can be high-level abstractions. Like in the case of an autonomous vehicle, this can be something like a decision of whether or not to stay in our lane or make a lane change. Or this can be something a little bit lower level, like a command, like a set speed for a cruise control. But regardless, this is basically going to be some sort of reasoning or some sort of abstract decision. And this gets passed down to our trajectory or motion planning module. So this is going to take these commands or these actions and try and turn them into the physical motion or movements of the robot. So if we are told that we should change lanes or consider change lanes, this will actually be saying how we should do it. So what is the trajectory and the motion that this robot should actually follow and move? So this planning system not only needs to consider the obstacles and constraints from the perception system, as well as the guidance from the decision making, but it also needs to be able to understand the physical constraints of the vehicle. So when we're considering these sorts of trajectories, we want to basically, hopefully we are already considering the fact that our car can't move directly side to side, but we need to have feasible or achievable paths. So the output of the system is going to be something like some trajectory that we can follow and often looks into the future. So this planning aspect sort of looks forward in time and tries to think about how we will move and how we will navigate through the world. Okay, so these decision-making and trajectory planning pieces are some of the most sort of common instantiations of AI as they relate to robotics. So this really tries to work on how we reason about and how we understand basically human-like behaviors or human-like motions. So the goal of decision-making and planning is often to try and achieve human-like intelligence. So when we think about these modules in blue here, this perception and decision-making and sort of motion pieces all kind of make up the brain of our robot. So this sort of puts it all together and really thinks about sort of this reasoning piece. But since we are working with a physical system, we need to think about how this can pass down to the hardware. So typically all this gets passed down to some low-level control. And this low-level control is basically going to be the middleman between the output of the decision-making and planning to the hardware itself. So basically, this is going to convert these planned motions into inputs. So if we think about the car itself, it's basically going to be the piece that turns a planned path, say a particular lane change or how you will make a right turn, and turn it into the car inputs. So this would be your steering, your throttle, and your brake. So this will sort of be this very fast reactive decision making that will basically be actually maneuvering the vehicle itself or the robot in general. So all of these different pieces need to come together and they get executed on your compute platform. And depending on your robot, this may or may not add some new capabilities or new constraints. So if we're thinking about this research vehicle as is imaged here, you can imagine that if we're trying to run all these algorithms and collect all this data and run all these things, if we want to run more stuff, we can just add another computer. So typically we're not very limited in the computational power. However, if we're thinking about a slightly different robot, say like a quadcopter, we'll often need to consider a little bit more about basically the computational or processing constraints, since we need to be very lightweight, and we'll have to think about basically some alternatives for that. So depending on basically the constraints of your system, you might not only need to think about how you can efficiently run all of your algorithms, but possibly even start connecting with some folks on the computer architecture side, so you can really think about how to get basically the most bang for your buck on the computational side. So as I said before, one of the key things about a robot is that it doesn't just sort of operate in isolation. This isn't just an algorithm that's running in the background, but you are actually interacting with your environment. So you are influencing, you're sort of making actions and changing how you see things. So one of the important things to consider is how you model and understand what's going on in your environment. And when I say environment, I'm often sort of being all-encompassing, but one of the key things in the environment is often other human agents or other systems that you might be interacting with. So oftentimes, if you're in a very dynamic setting, you'll need to consider these different or build in different models for these human agents and think about basically how your actions might influence them and take that into account in your reasoning. So really thinking about how to predict and understand the consequences of things in the world. So this is an important piece when you really want to think about how you can have sort of optimal actions and motions. So last but not least, another key piece to think about is the simulation and validation components. So as you're putting together this full system, you really need to be able to test and understand whether or not your system will work before you go through all of the effort to deploying it and sort of letting it run wild. So by having a good simulation of your system, you can kind of start understanding where it will break, how good it will actually perform under different scenarios, and kind of figure out some potential dangers or consequences of your system. And this is actually a very hot area right now, and it's tightly tied to things like game design. So as folks are thinking about how to design these decision-making and learning pipelines, simulation becomes an increasingly important role as we think about how we can sort of build up these capabilities in simulation before releasing them into the wild. Okay, so these are all the different components that we basically need to design a single robot. And again, these basically all have to loop together. As I mentioned before, one of the key things about a robot is that it kind of has this sense, think, perceive pipeline. So we're constantly thinking about how we can sense, understand, and act in the world and how this will change everything. So our actions will basically change and influence what we perceive. So this full system has to come together to build our system. Okay, so at least at a high level, hopefully we have some idea of what has to go into our robots. So now we can start thinking about some of the challenges and things that are basically inhibiting robots today. So even though humankind has been studying robots for a very long time, there are still some fairly big open challenges. So as I mentioned before, and I hope you guys can see my mouse here, this idea of computer vision, or basically this perception module, where we're trying to give the robots the capabilities to basically perceive the world as we do, is still a very big challenge. And one of the reasons why it's so important is because it influences basically everything downstream. So it's sort of one of these big pieces that is still an open, a current limiting factor. Another key point is, I'll kind of group these two together. So when we think about grasping and manipulation, so this is basically if you think a robot that needs to pick up objects, so it needs to be able to grasp and manipulate different items. This is something that's very challenging because you both need to have basically all the different pieces that we talked about before, but you also need to have a really good understanding of contact dynamics in physics. Similarly for mobility and locomotion, when we're thinking about robots that perhaps aren't wheeled, that have legs, so thinking about the different dynamics of these systems and how we can design the algorithms to accommodate basically all these different sort of physical pieces that are going on is still a huge challenge, just because the physics themselves is still really, really challenging. So there's some really interesting math problems that then influence the sort of algorithm and intelligence that we can then design. So as I mentioned in the very beginning, I think a lot about how we can design these systems that have to interact with humans. So we'll focus on some of the challenges inherent in this human-robot interaction for just a little bit here. So one of the things that I think is really interesting about human-robot interaction is that it's really a key and important piece when we start really thinking about deployment. So when we think about these systems, we often want to think about how they'll operate in the real world. And at least in my view, I think one of the big challenges is thinking about how they will interact with the people there. Okay, so I think just as a quick motivation for why this is hard, I'm going to show this quick video. So this is just a human driver driving at an unstructured intersection. And I think this does a really good job of just capturing the fact that the real world is really, really hard. So despite the fact that there's tons of effort going into autonomous driving and developing autonomous systems, figuring out how to handle these sort of crazy clustered scenarios is still really, really challenging. So despite all this work, we haven't quite figured out how people typically interact and navigate these scenarios. So this is just sort of an embodiment of one of the big open challenges. So despite all of the effort, no autonomous vehicle today can handle a situation quite like this. So as I mentioned, one of the big goals is we want to start thinking about how we can move from sort of today's most common robots, like on the factory floor, to these really cluttered human, sort of human-dominated settings. So I mentioned that the most or majority of these working robots today are operating in these manufacturing settings. And as you can sort of see in this video here, these robots are typically in cages, or they're very isolated from people. So they're basically in these really, really tightly constrained settings. And if a person comes nearby, typically they will just stop moving. And that's basically how they operate. So there's basically no sort of freedom in how they'll interact or could interact with people. So again, this is very different from the real world, as we saw in the last video or in this crowd here on the right, where we typically have people interacting, and we really want to think about how we can move to the spaces where people are actually operating. So thinking about how we can start interacting with these systems. So I think one of the big things we want to start thinking about is how we can make these robots that have these sort of rigid, repetitive tasks and start moving them over to interacting in these sort of cluttered spaces. And I think one of these sort of maybe homework assignments for all of you is to think about how the different pieces and modules that we talked about that go into a robot can start sort of facilitating these sort of crazy or more cluttered scenarios. So how can we basically make improvements in all these different people to move from these factory floors to these public spaces? So in this last minute, I'll just talk a little bit about some of the work that I do to hopefully help close some of this gap, or these gaps here. So first, I work on sort of the strict robot side, so really thinking about how to design resilient robots. So this is the camera view of that agricultural robot that I saw before. And this video is looping, so it's a little bit hard to see, but at some point this robot will get stuck. Here it is stuck, and it needs to eventually call for help because it can no longer move. So if you actually see, there's this plant that's in its way, blocking its view. So part of my work is really thinking about how we can improve the decision-making, planning, and control pipeline so we can recover from these potential failures and anomalies. Also on the robot side, I really think about the safety components. So again, leaning into some of those simulation components. So thinking about how we can design for safety as well as assess it. And one of the key pieces that goes into that is really thinking about how to model the different human agents. Because again, if we want these systems to go out into the public and really think about how to interact with these agents, we need to have a good understanding of how these people will move through space. So this is a quick example of a small autonomous vehicle that we have where we're predicting how this human will move, and we're planning our motions around that. Similarly, we think about more rigorous interactions, so not just sort of guaranteeing safety, but really thinking about how the robot can maneuver around the people. And it seems like that video was jumping again, but this is our crowd navigation robot that tries to maneuver around people and understand its influence on them. Okay, so with that, I would like to quickly thank my group and all of my lovely sponsors for this work. And with that, I'll take some questions.
Thank you. I guess one question I had here would be, where do you see the future of robotics like this going? Maybe in terms of the limitations or coming past the limitations you discussed earlier.
Yeah, great question. So I think one of the big things that we'll see is, as I mentioned, there's sort of this push to move from these highly constrained environments to more public spaces. And I think we're starting to see that a little bit more, like with things like delivery robots and some of the like cleaning robots getting a little bit more advanced. And I think that's some of the first steps that we'll take. I guess, as I mentioned, there's been a ton of work in autonomous vehicles. And I'm sure, I guess one of the big questions I always get asked is, when will we have our fully autonomous vehicles available to everyone? I guess with the exception of Tesla. But I think, at least in that example, one thing that we'll sort of see, in my opinion, is more gradual levels of autonomy that goes up. So cars are getting smarter and smarter, and they're having more and more sort of assistive systems. And I think that's often how these things sort of get introduced. So they start with sort of small things, or start in very controlled settings, like the Roomba, and then they slowly get more and more advanced.
Kind of going off of that, for people who criticize this field or say that the furthering of automation like this is a negative thing for society, how would you combat that?
Yeah, so I think one of the big concerns is, I think one of the biggest concerns is often about people losing jobs. And I think that's not as big of a concern as people typically think. So in the case of manufacturing, the jobs that robots take are typically the ones that humans don't want to do or can't do. And I think one thing that we'll see is a shift from a strict replacement to just a shift in roles. And I think part of that is, to reiterate that, I guess, or to restate that, as I mentioned, the current sort of state of, say, manufacturing robots is they're sort of in isolation. They don't work near people, they cannot work with people, and all of this. And I sort of see this shift to where people are more interested in thinking about how we can have better collaboration, or figure out how these robots can actually physically work together. So instead of having to do these rote repetitive tasks that people probably are not that efficient at doing, they can move to basically supervising or guiding the robot and doing these things that people are typically better at. So I see this as more of a shifting role and not necessarily something as a strict switch or something that is immediately bad.
Great. A bit more of a fun question. What is your favorite application of robotics like this that you either worked on or you've heard of before?
My favorite application. Well, I have worked on autonomous vehicles for the longest, so I think that would be, that's probably my default favorite. But since moving to Illinois, I think probably because we're surrounded by the corn and ag, I think the agricultural robot stuff is actually really, really interesting. I've learned a lot more about corn in the past 2 years than I thought I would.
Nice. We had one question here in the chat. You mentioned a lot of different kinds of studies important to your research, like stimulations, hardware, decision-making. Would you say your day-to-day work is very collaborative?
Yes, yes. And actually, this is one of my favorite parts about robotics, is it really pulls from a lot of different fields, not just computer science and engineering, but also psychology, bio, mechanical design, HCI. It really pulls from all different kinds of fields because it's typically such a very, they're very complex systems if you really want to focus on the full system. So yeah, all of my projects have people from different fields. And yeah, there's lots of different things going on. So again, my favorite part about it is that I feel like I'm constantly learning and I get to interact with lots of different people.
Nice. One last question we can close off on, I guess, would be for students who find this really interesting and want to see a future of themselves doing this, what advice would you give them, or what skills would you say that they should focus on?
So I think depending on which area of robotics you want to go in, they kind of have different areas of specialization that you can go into. So I think a lot of it is sort of up to you. So if you're really excited about design and interaction, then there's a whole area of study in robotics on basically perceptions and social interaction. So you can go into sort of those areas and specialize there if you'd like. If you're really excited about math and physics, then you can go into that and you can start studying this grasping and manipulation and really thinking about these sort of contexts and how we can enable the robots to pick up and do different things. So I think again, this is one of my favorite things about robotics is there's so many different aspects and different things that you can do. It's really sort of up to you to pick out your favorite spot and kind of delve into it. A lot of robotics today does require some programming, and that's something that's fairly easy now to pick up on your own. So I think brushing up on some programming skills is always good. But again, it's sort of this beautiful thing that you can kind of do what you want with it.
Thank you so much for your talk, Professor Driggs-Campbell. It was really interesting, and I think a lot of students will be able to gain a lot from it.
Awesome. Thanks for having me again.